When we try to build artificial intelligence that can improve itself, we hit a structural ceiling. If an AI writes better code for a base system, it needs a higher-level metasystem to improve the writer. And to improve that metasystem, you need another layer, and another, leading to an infinite regress of meta-layers trying to outscale each other. Researchers recently bypassed some of this friction with the Darwin-Gödel machine, or DGM. It proved highly effective at recursively improving pure coding agents. It works by starting with a single coding agent. That agent generates variants of its own code, evaluates those changes, and keeps the successful versions in a growing archive, treating each improvement as a stepping stone for the next iteration. But the system relies entirely on a fixed, human-engineered mechanism to generate its self-improvement instructions. The agent can write better code for the task, but the logic determining how to improve is completely uneditable by the AI itself. Because that meta-level agent is locked, the system's capacity to evolve is bounded by the human designers who wrote its initial instructions. It creates a hard bottleneck on how far the system can scale its own intelligence. To achieve open-ended progress on any computable task, a system must merge its ability to solve problems with its ability to improve itself. Researchers have introduced a framework called the Hyperagent. This architecture integrates the task-solving agent and the meta-level improvement agent into a single editable Python program. This creates a capability called Metacognitive self-modification. Since the system is unified, the AI evaluates its own task performance and can then rewrite the actual algorithms it uses to propose and apply future modifications. It edits its own learning mechanism. The AI completely stops searching for specific task solutions. Instead, it continuously optimizes its own underlying search mechanisms. Previous architectures, like the DGM, rely on a premise known as the domain alignment assumption. In software engineering, evaluating code performance and writing self-modifying code require the same set of skills. An agent getting better at writing Python is simultaneously getting better at writing Python to improve itself. When we apply this to non-coding domains, that alignment breaks down immediately. Consider the task of simulating peer review for machine learning papers. An agent that is highly capable of summarizing a research PDF does not naturally acquire the skills required to rewrite its own underlying Python codebase to refine its review criteria. The two tasks require entirely different proficiencies. This bar chart displays the performance of various self-improving agents on the paper review task. The original DGM, shown here as the red bar, rests entirely at 0. It fails to generalize because its instruction mechanism is rigid and tailored strictly to coding. Without the ability to edit its own cognitive architecture, domain misalignment stops the self-improvement loop entirely. Overcoming this requires a specific change to the system's architecture. In the original DGM, the task agent and the meta agent governing its changes are strictly separated. The instruction generation sits in isolation. Because it's handcrafted, the system's feedback loop deflects off it. The AI cannot alter the logic controlling its evolution. The Hyperagent resolves this by fusing the task agent and the meta agent into a single entity. The feedback loop now targets the entire program. The system evaluates its performance and can edit the foundational instructions that dictate how it improves. Because the Hyperagent operates as a Turing-complete Python file, any line of its own meta-logic can be rewritten by the agent. Making the meta-level editable removes the learning constraints initially hard-coded by human engineers. It wrote a Python class called Performance Tracker. Within this code, it built a moving average function designed to analyze its historical trends over time. It also created a persistent JSON memory bank. It used this file to log causal hypotheses, flag when it made a critical issue regression, and establish guardrails to prevent repeating past mistakes. These scripts represent actual structural improvements to the learning process itself. The agent built standalone diagnostic tools to measure the effectiveness of its own code edits. Metacognition enables an AI system to invent standard software engineering practices so it can aggressively manage its own evolution. The true test of meta-learning is whether the self-improvement infrastructure engineered by the AI can transfer to a completely unrelated domain. To measure this, an agent that had just optimized itself for quadruped robotics and paper review was transplanted into a new environment and tasked with grading Olympiad-level mathematics. We evaluate this transfer using a metric called Improvement at 50 Iterations, or IMP at 50. which tracks the performance gain achieved over the initial agent after 50 cycles. This bar chart tracks improvement at 50 iterations. The original DGM, transferred from previous tasks, registers an improvement of 0. The locked meta-agent failed because it only learned domain-specific shortcuts for robotics and paper review. It never learned generalized algorithms for how to improve. This chart shows the Hyperagent under the exact same conditions. It achieves an improvement score of 0.63. Because the Hyperagent had autonomously built generalized memory and tracking tools, its acquired ability to self-improve successfully transferred to a completely new domain. These universally transferable metaskills introduce a new dynamic into machine learning. It allows for compounding self-improvements. The system can take lessons learned in one environment and use them as a hardened baseline to accelerate its learning rate in the next. The naive Hyperagent is blue, while the transferred Hyperagent in orange deploys pre-existing tools to bypass trial and error, locking in a higher baseline. Combined with the Proof Autograder tool, this approach scales rapidly over 200 iterations, breaking away at the top of the chart. In this final chart for Olympiad-level math grading, the Hyperagent clearly surpasses the dotted line representing the human-engineered industry baseline. The system is bounded by available compute limits and the overarching tasks defined by human operators. By bypassing the human-engineered meta-bottleneck, the Hyperagent architecture establishes an empirical, structurally sound step toward genuinely self-accelerating artificial intelligence.